Yes, hi. Welcome to my talk on the joint work I did with Thomas this year, Thomas Schneider, Properties of Modular Notions and Atomic Decomposition. I have to give you a little bit of backstory before I get to our motivation. So modular extraction is the problem given a T-box T in the signature sigma, that is a subset set of concept and role names. We want to extract from T a subset M that contains all knowledge about this signature. So formally, you would write this as you can capture the notion as follows. We have a signature and two T-boxes are inseparable with regard to sigma if they entail the same second order sentences written just using sigma. And then a module of T is a subset M of T such that M and T are inseparable from each other with regard to the signature. So they entail the same second order sentences written in sigma. Usually model inseparability is not decidable even for description logics of moderate expressivity. However, there are good approximations. These are called modular extraction functions. Those are functions that map any signature sigma in a T-box T to a module of T. And there are many examples that have been developed, different approaches to module extraction. For example, locality-based modules, Datalogbased modules, lean kernels, deductive modules, and many more. So there's a variety of module extraction functions. But in ontology modularity, there's another problem. So the first problem we just talked about, extracting a single module of an input T-box given a seed signature. The second problem is the modularization of an ontology, which is just given T. We want to find any structure within T that captures the modular dependencies between axioms. For example, we want to group axioms together and find a dependency relation, much like a reading order, so that developers can navigate through their ontology and find dependencies between axioms. Now, while modular extraction is formally definable, modularization is not. There are many different approaches to that. And one of these approaches with strong logical guarantees is atomic decomposition. Atomic decomposition is such a modularization approach that develops a dependency relation between axiom sets. And to do so, it calls another module extraction function, the problem that we just spoke about before, linearly often, and then we have a representation of exponentially many modules. I can't go into the detail of atomic decomposition, unfortunately, because of time constraints. Just take away that we need a module extraction function to compute the atomic decomposition. And when the atomic decomposition was firstly developed, it was based on locality-based modules, which are also the first module extraction function that has been developed. Last year, however, the original authors showed that any module extraction function can be used as long as it satisfies certain properties. However, there's a variety of module extraction functions, as I just showed you, and for most of these, it is unknown whether they meet these requirements. So this is where we start from. We have a cool algorithm, the atomic decomposition. We want to use it, maybe with different module extraction functions that come with different properties. It can be used for different logics and so on and so on and so on. So I have to give you a quick overview of the properties that we're talking about. These properties are not only relevant for atomic decomposition, but for module extraction in general. Many applications depend on these properties additionally to inseparability. The most well-known property is self-containment, which is M is not only inseparable with regard to the seed signature from T, but also with regard to its own signature. So we combine the signature of M and the signature that we used, this signature, and M and T should still be inseparable with regard to that signature. And the idea behind that is that we don't have to remember the seed signature anymore. So if there's any concept name or role name occurring in M, we know that M captures the knowledge about that has been stated in T about this concept or role name. And we don't have to look back whether it was in the C signature or not. There are many more properties, and I just name them because they're important for our results, but I can't get into any details. Just visit our paper and have a look there if you're interested. So many might know about weak or strong depletingness. Preservation of justification is another important property. Then there's monotonicity. A module extraction function can be monotonic in the input signature or the input T-box. Weak, strong superpotency is just used for atomic decomposition. And there are a lot of other properties. The ones we focused on have been the ones that are important for atomic decomposition, and these are self-containment, monotonicity in the seed signature, and superpotency. And we can also group these properties. The first three are logical properties. They guarantee certain entailments of second-order sentences, while the other properties are behavioral in the sense that it's only dependent on the module extraction function itself. For example, monotonicity does not entail any logical guarantees. And what we did first was we had to look at these different properties and investigated how they interrelate with each other. So, one last thing. I'll just talk about self most of the time because it's the one I explained here, and we did many investigations for the other properties, but I don't have time to go into every detail here. So interrelations between the properties were our first main result. And it's quite obvious that the strong properties, strong depletingness implies weak depletingness, and strong justification preservingness implies weak justification preservingness. These are quite obvious to see. However, we can also see that justification preservingness is stronger than depletingness. So if you have a module that is justification preserving, it's also depleting. And also justification preservingness is stronger than self-containment. So if you have a justification preserving module, it's also self-contained. Interestingly, these logical properties can also be entailed by just behavioral properties. So if I have a module extraction function that is just monotonic in the input T-box, which is a very easy property to see, it's just if T1 is a subset of T2, then also the module to T1 should be a subset of the module to T2. We are justification preserving. So the logical properties can be are implied by behavioral properties, which are very easy to prove. And the same holds for the strong properties. If you take another property that is also behavioral, strong superpotency into account. And these interrelations might seem not so interesting at first glance or not so impactful, but indeed, for example, locality-based modules, which are the most commonly used module extraction function, are monotonic in the input T-box, and therefore we showed just by these interrelations that they are also justification preserving, which is the first time this has been shown to the best of our knowledge. Many module extraction functions use some kind of iteration process to ensure the strong properties. And for atomic decomposition, we are interested in one of the strong properties, which is self-containment. And we can actually generalize this approach of iteration. So given any module extraction function that satisfies some weak property, we can construct an iterative extension that also satisfies the strong variant. And this comes only with polynomial overhead. So our picture looks like this. If I have a justification or depleting module, then I can also construct a module extraction function that extracts strongly depleting or strongly justification preserving modules. And also if I have any module extraction function, I can construct a module extraction function that is self-contained. So the first property for atomic decomposition can always be guaranteed self-containment. We encountered another problem. Various module extraction approaches require the input T-box to be normalized. For example, Datalogbased modules or reachability-based modules. However, for atomic decomposition, as it is meant for ontology developers, we are interested in modules of the original ontology so that we can compute the atomic decomposition of the original ontology and not of any normal form of that, because a developer does not want to look at the normal form of an ontology. So there's another problem, and that is the problem of denormalization. We have to denormalize a module that has been extracted using a normalized T-box while preserving the properties. So the denominalization should keep self-containment, for example. And there is a known result. Yeah, thank you. There is a known result by Amas Romero et al. That showed that depleting and justification preserving modules can be denormalized. However, we showed, and this is our third main result, that under mild assumption, the strong properties, self-contained, depletingness, and strongly justification preservingness are as hard to denormalize or preserve during denormalization as module extraction itself. So any denormalization function that preserves these is a module extraction function itself. And therefore, the iteration process that can be used to make module extraction function self-contained should come after denormalization. So with some other tricks for the other properties, we actually end up with this theorem, which is our last main result. Any module extraction function that is just monotonic in the input signature can be extended to a module extraction function that can be used to compute the atomic decomposition of an ontology. And in natural cases, this even holds if M requires some form of denormalization. Finally, we had a case study for Datalogbased modules. They are denormalization-based module extraction function, and they come with some benefits. They can be computed for any fragment of first-order logic, not only for description logics. Instead of, for example, locality-based modules can only be extracted for description logics. And they also approximate 4 different inseparability relations. I only showed you model inseparability. And they are tailored to specific use cases. So, for example, Boolean query answering. And with our last main result, we can also extend them for use in atomic decomposition. So for Outlook, we want to evaluate our extensions on real-life ontologies. And also, we want to apply our frameworks to other module notions. For example, reachability-based modules. Yeah, thank you. Are there any questions?